Good morning, and thank you for joining us for our live talk with Dr. Stephen Wilkins, who is a reader in astronomy at the University of Sussex. As many of you will know, today is the first day of World Space Week, which is an annual international celebration of science and engineering. It's great to see so many schools and individuals joining us today, and we're sure you're going to have a great time. You're in for a space treat, as Stephen will speak about the famous James Webb Telescope, designed primarily to conduct infrared astronomy. It is currently the largest optical telescope in space, which serves thousands of astronomers worldwide. He will also tell you about his own career path and the routes he took to where he is today. You'll have the opportunity to ask questions, so please pop them in the chat, and Stephen will aim to answer as many as he can at the end of the talk. You can also email us any questions post-event to Ask an Ambassador, also detailed in the chat. So that's enough from me. I will now hand you over to Stephen. Good morning, Stephen.
Good morning, thank you. Welcome everybody. It's great to be speaking to you this morning on almost the beginning of World Space Week here. Today I'm going to tell you a little bit about a project which is very exciting, something that I've been working on for a long time, in which some of my colleagues have been actually working on for a couple of decades now, and this is the James Webb Space Telescope. But before I do that, I just wanted to introduce myself very briefly. So I actually grew up in Leeds in Yorkshire, so up north. I think many of the people on the call are probably from down south in Sussex. I was then an undergraduate student in physics and astronomy at the University of Durham. I then did my PhD in astronomy at the University of Cambridge, and then I moved to the University of Oxford, where I worked as a researcher for a few years. And then almost a decade ago now, I moved to the University of Sussex, where I've been slowly making my way up the university hierarchy. So I started off as a lecturer, then became senior lecturer, and now I have this funny title of reader at the University of Sussex. So that's my title. So I'm a reader in astronomy, but what this actually means is that I teach, I do research, I do administration, so I look after the department, and I do lots of public engagement like today's talk. So I have another couple of roles as well. So I'm currently head of astronomy at Sussex, so I'm kind of responsible for the 40 or so astronomers here, and I also direct our outreach and public engagement program at the university. So my job routinely involves doing lots of things, and this is one of the reasons why I really enjoy my job a lot, because it has a huge amount of variety. So from a day-to-day basis, I might be designing computer software to actually, analyze some of these great observations. I might be writing up my discoveries. I might be making presentations, sometimes presentations like this. I might be organizing people. Last week, I actually spent a few hours organizing our welcome party, which was a nice welcome change. And then, this was mostly before the pandemic, but I would do lots of travel. So we would often go around the world to talk about our research and work with colleagues. So I think this is one of the really great bits of my current job, is that it has this huge variety, and there's always something different from a day-to-day basis. For example, you might find yourselves having to wake up early and speak to a bunch of students at 8:40 in the morning. So what I'm going to do now is I'm going to tell you about this project called the James Webb Space Telescope. And I'm going to frame this with the phrase first light. And this is because this phrase actually means two quite different things, which overlap in my case for this telescope. So when we talk about first light of a telescope, this is the first time we use that telescope. Okay. But when we talk about the first light epoch, okay, or era, this is the period of the universe's history when, things started happening in our universe. So when stars first started forming. And we're in a really, special situation that we've just had first light of the James Webb Space Telescope over the last few months, right? And we're going to start using it to study this first light epoch. And so that's what I really care about. But before I talk about, some of these and what we've seen already, I just want to introduce you to the wider project. Okay, so this is a computer model of the Webb Telescope, or the James Webb Space Telescope, or JWST. And this is really the world's next flagship astronomical observatory. It's a successor to a very famous telescope called Hubble, and one which is slightly less famous called Spitzer. Okay, so it's, this is now showing these three observatories to scale. So the ones on the left were the ones that we previously had, and we now have Webb on the right. And you can see that the most striking feature of Webb is that it's much larger. Now, this allows us to see fainter things, it allows us to see further away, and it allows us to see things in more detail. Okay, so you can get an idea here that Webb on the right is actually 50 times larger than Spitzer down at the bottom and 5 times larger than Hubble. And so this really allows us to transform how we can view our universe. But most importantly, the Webb telescope, unlike Hubble, but actually like Spitzer, is not designed to look at the light that we can see with our own eyes. It's actually designed to look at the infrared. And there's a whole load of really good scientific reasons for that, okay, which I'll come back to a little bit later. Just worth pointing out here that Webb is actually one of the most complex and expensive scientific projects of all time. This has been in development for more than 20 years and so far has cost around $10 billion. Okay, so arguably Webb is actually the single most expensive thing that humanity's ever created. The people who work on the International Space Station may disagree there, but that's really a lot of smaller things glued together. Okay. A really, really important other point here is that although the media may have you believe that this is just a NASA project, actually this is your project as well. So the Webb telescope was built and designed by the combination of NASA, the European Space Agency, our space agency, and also the Canadian Space Agency. And there are hundreds of universities and research institutes and thousands of scientists across the world, including here in the UK, who have contributed to this project. In particular, there's really strong contributions from the UK on the leadership and development of arguably Webb's most advanced camera. This is something called the Mid-Infrared Instrument, or MIRI. Okay, this was actually, mostly designed up in Edinburgh and then tested across the rest of the UK. I just want to point out here that this is not just something for astronomers. In fact, a whole range of people in different careers have contributed to this project, not just astronomers. So I'll now just go through a list of some of the people who have contributed to Webb over its lifetime. So obviously, first of all, we do have the astronomers. These are the people who kind of said what they wanted for our telescope and are going to be the ones who routinely use it. Okay, but arguably they're not actually the most important. Perhaps the most important are the engineers who actually went ahead and built this to the astronomers' specifications. So these are people who have designed the telescope, designed the electronics, etc. Alongside the engineers, you have technicians. So these are people who are maybe training to be engineers or more of an entry-level post. These are the people who actually did the hard work, so actually had to build the telescope itself, which is an incredibly complex thing. We also have software engineers, because these days, your software is almost as important as the hardware that you have. And so we've had people writing computer software for, the last 10 years or so to actually use and analyze the images from Webb. And then none of this would be possible without having people to administrate everybody else, right? In isolation, none of these groups can really do anything without being administered. And so this is why we need, a whole layer of administration, going from people in charge of organization to, down to clerical support. All this makes the project possible. And then we also have digital creatives. I write this because I'm now sat in Brighton, which has a huge digital creative industry. But many of the pictures that I'm going to show you have been, transformed from what we get from the observatory into some of these beautiful images. And they have a really, really important part in actually promoting the mission to the wider public. Now, after many, many years of delays and many years of development, the Webb telescope finally launched on Christmas Day 2021. In a way, this is a little bit bittersweet to me, because prior to it launching on Christmas Day, it was due to launch a more convenient date, and we were going to have a huge party. But in fact, I ended up watching the launch from a tiny little screen on my iPad while I was peeling carrots in my in-laws' house in Leeds, which is not exactly how I wanted to celebrate. But at the same time, getting Webb that day was one of the best Christmas presents you can imagine. Okay, so first light. So what I'm going to show you now is a collection of pictures that have been taken from the observatory. I'm going to talk you through them quite quickly so I can talk about some of my own research. These are just some of the ones that I found really, really stunning over the last couple of months. And this really is just over the last couple of months. We've only really had this observatory since the middle of July. So we're now only about 2.5 months in to its 20-year mission. Okay. So first of all, hopefully this is familiar to most people, but this is Jupiter. Okay, down at the bottom right, you can see the Great Red Spot. Okay, remember this is an infrared picture now, so you're not seeing exactly what you'd see with your eye. You can see this pair of two dark spots. Okay, this is actually where we have a shadow of one of Jupiter's moons, casting a shadow on the surface of Jupiter. Okay, you can see the wonderful bands in Jupiter. So this is, visible even with a small telescope. You can see these, bands, which are different storm systems. And you can see kind of at the interface between the two bands, there are these wiggles, and these are all storms. Outside of the actual disk of Jupiter itself, you might be able to just see a very, very faint oval kind of going around. This is actually a tiny ring that Jupiter has. So it's not just Saturn that has a ring system, Jupiter also has a little ring as well. And on the far right-hand side, around the middle, you can also see one little dot as well. That's one of Jupiter's many moons. Okay, so this is a really transformational image of Jupiter, which was taken very quickly by Webb. Moving a little bit further away now, what we have here is the leftover remains of a star that has died. Okay, so this is an object called a planetary nebulae. Specifically, this is the Southern Ring Nebula. And what you're seeing here is you can just about see the star in the middle. That star is on its way to dying. And as it dies, it sheds all of these layers of material. Now, this is actually really important because these layers of material that you're seeing around the star are enriched with all of the heavy elements that go on to make you and me. So things like oxygen, carbon, nitrogen. And it's only really in these objects, these stars dying, that the universe creates these elements that are vital for our own existence. Going a little bit further away now, we have my new favorite image of all time. This is a patch of our own galaxy called the Carina Nebula. And what you're seeing here is a giant cloud of gas and dust. And inside this cloud of gas and dust, you have new stars and new planets being formed every day. Okay, so this is really a stellar nursery where we expect stars and planets to come from. This is a very similar object. So this is an object kind of scarily enough called the Tarantula Nebula. And what you're seeing here is actually a new cluster of stars that has recently formed. So right in the middle of the image, you can see actually thousands of individual stars. These are all young stars that have just formed from all this surrounding gas and dust. And you can see they've left this big hole in this cloud of gas and dust now. Moving a little bit further away again, what we have here is a collection of 5 galaxies. Now, these 5 galaxies, 4 of which are actually interacting with each other, that means they're crashing into each other and may form a new galaxy at the end of this process. But as they crash into each other, they actually trigger these huge bursts of star formation, again, creating new stars and planets. And then here we have JWST's or Webb's very first deep image. So what you're seeing here is a special patch of sky called SMACS 0723. This is actually a cluster of galaxies, so that's what you're mostly seeing. And this is a huge collection of galaxies, which themselves are collections of millions or billions of individual stars. And in this image, what we're actually seeing is galaxies stretching across most of the history of the universe. Okay, so let's then talk about what I actually work on, which is the first light epoch. So as we look out into the universe, we don't see it as it appears right now. This is because light takes some time to actually travel to us. So for example, when we look at the moon, you're actually seeing the moon as it appeared around 1.5 seconds ago. Okay, when we look at this middle object, this is another one of my favorite objects called the Pillars of Creation. We're actually seeing this as it appeared 6,000 years ago. And the one on the right, this is a galaxy called Centaurus A. We're seeing this galaxy as it actually appeared 30 million years ago. So this is now well beyond the history of human civilization on the Earth. But we can take this even further. With observatories like Hubble and now Webb, we can push all the way back towards the Big Bang, okay, 13 billion years in the past. So this last image that I showed you, this bit of sky called SMACS 0723, then actually contains galaxies stretching back over most of the history of the universe. So some of the little blobs in this image on the right are actually galaxies that we're seeing when the universe was incredibly young, well before humanity had emerged and even well before the sun had even been born. Okay, so this image just here on the right is this almost record of the entire history of our universe. Now, what I do on a day-to-day basis is actually try and compare images like the one on the right with models. And so what I mean by model in this context is a simulation. So in these simulations, one of which I'm showing on the left in this little video, what we do is we take all of our understanding of physics. So for example, how stars form from gas and how gas cools. We put all of that understanding of physics into a big supercomputer. And what comes out the other end are these fake universes, these model universes. And so one of my big jobs is to actually compare these model universes with the real universe and see if we've got the physics just right. As you can imagine, this involves lots of coding on computers, but also lots of cool visualizations like you can see on the left. So this is the end of the presentation, but it's certainly not the end of JWST's voyage. In fact, this is only a couple of months of JWST data. In fact, what I've shown you today is actually only a couple of days of data from the telescope. We've had so much more already. Now, over the next few months, my team is soon going to be receiving new, deeper observations, allowing us to push further into the universe's history. But over the next 2 decades, we can only guess at some of the amazing discoveries that Webb will soon make. And I think many of the people on the call, barring the teachers, are in a position that you might one day be using the Webb telescope for your own research. It will be with us for that long and will be such a tremendous resource. Good morning to everybody. I hope you've enjoyed listening to me today, and do send some questions in if you have any.
Thank you, Stephen. That really was an informative and interesting talk, and I'm sure our audience has been inspired to think about their future career paths. Yes, there are questions coming in, so I will hand you over to my colleague Sophie to kick them off.
Okay, thank you, Lisa. So first of all, we've got a question through from 10C at the Weald of Kent School. Are the nebulae images also in the infrared region?
That's right. So all of the images that I showed you were actually taken in infrared. So these are not the colours that you would see with your own eyes. So what we've done here is actually colour these infrared images to allow us to see them and to actually, show differences there. And this is one of the places where we really need the, for example, digital creatives to actually make these beautiful images. So it is always a bit of a shame that they're not what we can see with our own eyes, but that's just the way it is. If we're going to learn about these objects, we need to observe them in the infrared.
Okay, great. So I've got a question. How is the data collected on the telescope?
That's a great question. So the telescope itself has a little hard drive. So it takes the data and it stores it to that hard drive, but then it's got to beam it back down to the Earth. And to do that, the telescope has got obviously an antenna, a transmitter, and then on the Earth, we use something called the Deep Space Network, which is a collection of radio dishes all around the world, which can receive these signals. And so once the signals are received there, then it then gets processed a little bit, but then is available for anybody. Well, most of the data is available for anybody all over the world to go ahead and download and analyze. So all of the data that I've shown you today is public data. If you're interested, you can actually go and analyze the original scientific images and play with them yourself.
Thank you, Stephen. I've got a question here from St. Gregory's 9A. How do you know the universe is 13 billion years old, well before human existence?
That's a really, really interesting question. So this is a problem that we've been trying to solve for almost 100 years. So our main constraint on how old the universe is from something called the cosmic microwave background. What this is actually light left over from when the universe was much smaller than it is today. And by analysing that light in detail, we can actually work out how old the universe is. But that's not just the only way that we can do this. We can also, for example, look at rocks on the Earth, and that gives us, one idea of a minimum age of the universe. So when we look at rocks on the Earth, we know that the universe must be at least 4 billion years old, because we know the Earth has been here that long. and then we can look at, you know, stars in our own galaxy. And when we look at we can age individual stars and work out how old they were, and we find that some of those stars are, you know, up to 10 billion years old. So there's lots of different ways we can constrain the age of the universe.
Okay. I've got a question from a student at Hadlow Rural Community School asking if the red spot on Jupiter always stays in the same place.
Well, Jupiter itself is rotating, and the individual bands on Jupiter rotate. So from our perspective, it doesn't stay in the same place because the planet is rotating, and it does move around a little bit. But, you know, Jupiter doesn't have a solid surface.
Okay. So I've got a question from Great Oaks Small School. How long did it take to build the James Webb Telescope?
Well, it's a difficult question, but we first started designing it more than 20 years ago. In terms of how long it took to build, it was at least a decade, but that obviously includes all of the testing as well.
So I've got a question 11D2 Willingdon Community School. They want to know exactly how far back can we see?
A really good question. So we're trying to do exactly this at the moment. So we think with the James Webb Space Telescope, we should be able to see some of the very first stars and galaxies to form. And so we think this will just be, you know, around 100 million years after the beginning of the universe. So that's kind of saying today we think the universe is about 13.8 billion years old. So maybe 13.7 billion years we'll be able to look back.
Hi. So a question from a student at St Gregory's. Have these images brought up any signs of life? And do you know what, there's two questions here actually. Do you know what the newest star is that has been formed?
In terms of signs of life, there haven't been any indications yet. But in fact, this is one of the things that Webb is designed to do. We're not talking about looking for little green men on planets, but what we will be able to do with Webb is look at the atmospheres of alien planets and actually tell you what those atmospheres contain. So that might reveal the existence of things like water and oxygen and ozone in those atmospheres. And if you have the right combination, there's maybe good evidence that you have life on those planets, at least in the form of, say, vegetable life. In terms of the most recent star formed, we don't really know because stars are being formed all the time. And the difficulty is, and this is partly one of the reasons why we have Webb, is that when stars are formed, they often form in the middle of these clouds of gas and dust. And it's only actually by looking at them in the infrared, hence with Webb, that we can actually see them.
Brilliant. Okay, so I've got a question from St Edmund's School. Do you employ animators to design the models?
Yes, so obviously the CGI models that you can see in the visualizations, these were designed by computer vision specialists. I think this was probably mostly done at the European Space Agency and NASA, but obviously that's an important part of the engineering and design stage. In fact, there's a whole section of engineering which is about making these visualizations.
Okay. Right. I've got a question from Brentwood County High School. Who names the stars?
This is a tricky one. So there is an organization called the International Astronomical Union who are kind of responsible for looking after the names of things. But when you discover something, you will often write an article and you will often, you know, refer to that object by a name, a catalogue name that you've given it. And so what ends up happening is that there isn't, you know, for most stars, most galaxies, there isn't one official name, there might be multiple names. Now, actually, some of my collaborators and myself, we got in a little bit of trouble recently because my collaborator named one of the galaxies that we discovered after his daughter. So he called it Maisie's Galaxy because it was discovered on her birthday. Now, some people told us off for that because apparently you shouldn't name things after people because it somehow violates what's called the Outer Space Treaty. But we did it for a little bit of fun and we're fine with it.
Brilliant. Okay, that's great. So I've got a question from Dartford Science and Technology College. How far is the James Webb Space Telescope from Earth?
Well, actually, unlike the Hubble Space Telescope, which is in orbit around the Earth, the James Webb Space Telescope actually orbits the Sun. It's at a very special point called the second Earth-Sun Lagrange point. And what's special about this is that even though it's further from the Sun, it still takes exactly 1 year to go around the Sun. Now, what this means is that the Earth and the Moon and the Sun are always in the same direction from the telescope. So this distance is 1.5 million kilometers away. So that's about 4.5 times the distance to the Moon. So it really is quite far away, certainly well beyond where humanity has ever gone before.
Okay. Right, I have it's a lot. It's got so many questions. St Gregory's 11. Sorry, St Gregory's School, I think. Do you think there is other life in the universe?
It's a difficult question to answer, but given how many stars and galaxies there are in the universe, and we're really talking about one with lots of zeros left after it, it would be a real shame and a real oddness if we were the only life in the universe. But at the same time, maybe that original spark of life is just so rare that this is, one of the only places where it's occurred. And this is part of Webb's mission to see, are there other planets out there that are A, potentially habitable, and B, do they actually have life on them already? And I can't guarantee you that Webb is going to give you the answer to whether there is life out there in the universe, but it will have the capability of detecting at least some life if it is, out there and relatively close.
Okay, thank you. So year 9 NSFG school, how long does it take for a star to die?
Depends on the star. So when stars are born, they are born with, different sizes. And generally, the bigger a star is, the shorter it lives. Okay, so the very biggest stars might only live a few million years and then they explode. Stars like the Sun will live around 10 billion years. And really, really small stars could live, trillions of years, much longer than the universe is old at the moment. So it really depends on the star.
Okay, thank you. Year 9 Northfleet School for Girls asks, do you use a series of individual images for the computer programs to predict changes?
Yeah, this is a really interesting question. So this is something called time domain astronomy. And we often will observe the same patch of sky many different times at different times of year. And by doing that, we can look for things that change over time. There are some, really important uses of this. So, for example, one of the ways that we detect planets around other stars is via something called the transit technique. And what this does is take advantage of little mini eclipses when you have a planet passing between ourselves or the telescope and its parent star. And that allows us to know that the planet's there, because individually planets are very, very difficult to detect because they're quite faint, especially when they're around other stars. Now, we can also use this same technique to find, different types of objects like supernova explosions. These are, when a star erupts in a giant explosion every now and then.
Hi. So I've got a question from Mr. Ward's class at St George's C of E. Is it possible to view planets in other solar systems and galaxies in similar detail to those in our solar system?
Not in the same detail, I'm afraid, just because they're so much further away. But certainly with Webb, we will actually be able to, actually image a planet, actually take an image of a planet. We're not yet having the capability that we could see things like continents or the Great Red Spot, but we can do, some really, really interesting technical techniques where we can maybe bring out details about things like continents on a planet if that planet has an ocean. So we're not going to be able to take really nice, beautiful images like we can have in our own solar system of these distant planets, just because they are so much further away, but we will get some information from Webb.
Okay, So this will have to be our final question. Sadly, we've got so many questions, which is fantastic, so much interest. So this is from the Weald of Kent Grammar School. What first made you interested in space?
I love answering this question because the first thing that got me interested in space was actually a computer game. This is a computer game that I played, I guess it would have been in the early 90s when I was still in primary school. And in this computer game, you could buy a spaceship and you could fly to different stars and visit different planets. What I really liked about this game is that they had realism in it. So they actually tried to create a realistic looking universe with realistic planets and realistic stars. So it wasn't just like an arcade game. It was, you know, built on the foundation of real science. And the detail in that kind of got me thinking about what all of these numbers meant, what it meant to have, you know, planets and moons and different types of stars. And in fact, today there is an updated version of this game, which I strongly encourage anybody to play because they've kept on to this tradition of being very faithful to the science. And this is a game called Elite Dangerous. Well worth playing.
Okay, that's brilliant. Have we got time for one more, Lisa, or do we? Yes.
Well, we've still got so many people on the call. Let's go for one final question.
Okay, so I've got a question from Brentwood County High School. Would you recommend buying a home telescope?
So I'm a really bad astronomer in that I actually don't have my own telescope. I think partly because I've been spoiled by being able to use things like Hubble and now Webb. If you don't have anything else, what I would actually recommend first of all is just buying a really good pair of binoculars, but really most importantly, making sure you can go somewhere where the sky is dark enough. So the problem in the UK is that there's lots of light pollution. And so it's actually, I think it's much better just to go somewhere dark and see, you know, the thousands of stars that you can see with the naked eye from a dark site, and then maybe build your way up to buying a good pair of binoculars and doing the same thing. You can start seeing loads of interesting objects. And then after that, maybe start investing in a telescope. So the problem is that relatively cheap telescopes won't really do anything and will probably actually just put you off astronomy because they're difficult to use and they won't give you very much. Whereas a good pair of binoculars, or even just, you know, looking at the night sky with your own eyes and looking for things like satellites and, you know, the planets, I think is a great way of getting started. And then I don't know how close you are to Sussex, but you know there are lots of amateur astronomy societies all across the country, lots of them in Sussex because of the dark skies here, and that will be a great place to go and, you know, get the first experience because there's often members there who have their own large telescopes and will be willing to and only happy to show people what you can see through them, and you can kind of use that to make your own decision in the future. But certainly, you know, a good pair of binoculars first of all, go to a dark site is what I would suggest first of all.
Thank you very much.
Great advice. Thank you, Sophie, and thank you, Stephen. Thank you so much for giving up your time. We know that you're a very busy man. And thank you very much for everyone for listening today. We're sorry we couldn't answer all your questions, but yeah, thank you for joining us and have a great Space Week. Goodbye.
Thanks, everybody. Thanks, Lisa. Thanks, Sophie.